Okay, hey, welcome back, class. This is our second lecture within the nuclear chemistry unit. Today we're going to be talking about types of nuclear decay and half-life. So in saying that, let's get to our objectives and then dive into what we're needing to do. So our objectives are, what I want you to understand before the end of the day is I need you to be able to identify the differences between alpha, beta, and gamma decay. I also need you to be able to determine the rate of decay and half-life of specific elements. Okay, so we'll show you how to do that in a bit, but those are our two main things we're going at. Now, in saying that, let's dive into our lesson. So radioactive decay. So in our last unit, we talked about nuclear chemistry, kind of understood like, hey, what's a stable isotope, what's an unstable isotope. Radioactive decay is the spontaneous breakdown of a nucleus into a slightly lighter nucleus. So these are going to be like unstable nuclei that are trying to make themselves into a more stable form. So that's why you're going to get these radioactive decays. They'll be emitting particles or electromagnetic radiation. So that's where we get radioactive decay. It's not just decay of breaking down, but it's radioactive because it's releasing stuff. Okay? And that way of releasing stuff, what is being released, that's how we're going to identify what type of decay, what type of radioactive decay it is. Just hang with me. A nuclear radiation is when something in the nucleus is not stable. So they're like, hey, let's get rid of this. So they get rid of whatever's in their nucleus, some part to make it more stable. Whether that's a proton, whether that's a neutron, whether that's something else. It's removing stuff from the nucleus to be more stable. An unstable nucleus that undergoes radioactive decay is called a nuclide. So now we got that terminology put out of the way, let's get into the specifics about radioactive decay. So why are we doing radioactive decay? Why do we need to learn about this in chemistry? Well, the purpose of emitting these particles, the purpose of releasing things from the nucleus or releasing electrons or whatever it is ultimately to make an atom more stable. There's many different ways we can do this, some of which are listed on the screen. Alpha decay, beta decay, gamma decay, positron emission, and electron capturing. Okay, so we'll talk about each one of these and how to notice them and how to figure out what's going on with these types of equations and what's going on with these types of reactions. So let's start with alpha decay. Alpha decay, the first thing you need to know is alpha particles. Okay, an alpha particle has two protons and two neutrons that are bound together. So we talked about with Ernest Rutherford, he shot alpha particles to figure out the existence of a nucleus. All an alpha particle is two protons and neutrons together, which is just a helium atom. So these helium isotopes with a +2 charge are the key indicators of alpha decay. If you see an alpha particle, it is probably going to go through alpha decay in some form or fashion. Okay. The bigger thing is alpha decay only happens though in heavy nuclei. In alpha decay, atoms need to emit neutrons and protons to increase stability. So what's happened is you have an atom, okay, and it has to emit or get rid of some protons or some neutrons to become stable. Well, then it's going to emit an alpha particle, which has two protons, two neutrons. And hopefully by then it's going to be a little bit more stable. So let's see what an alpha decay example problem is. Okay, so we have 210-84Po or polonium, and then it is going to decay and turn into lead 206-82 and an alpha particle. Some key things that we're wanting to see here is, first of all, we see that it is alpha decay because we have our 4,2 helium or our alpha particle. But I want you to see here is that if we take the number of protons on the right side of the equation and the number of protons on the left side of the equation, they're going to equal each other because of the law of conservation of mass. If we take our atomic masses from both sides of the equation, they're also going to equal each other because of the atomic masses. So our 210 equals our 206 plus 4. So one thing that's a key thing to be able to check with these types of equations is that they're always going to equal what they started with. So our polonium, we started with that. We're always going to have that many protons and neutrons at the end of the game. Okay, so alpha decay, 4,2 helium atom. Now let's go to beta decay. Okay, in beta decay, nuclides are above the band of stability and are unstable because of their neutron-proton ratio is too large. So we bring back in this band of stability again. So these atoms are more likely to be above the band of stability. Okay, that ratio is going to be above it. Because of that, they need to be able to get rid of some stuff. Their ratio is too big. So in order to reduce the number of neutrons within an atom can convert a neutron into a proton and an electron. So keep that in mind, and an electron. A beta particle is an electron emitted from the nucleus at some time during a radioactive decay. So let's think about this. Okay, we have an atom and it has so many protons, okay? It's just hovering around there, and then it's not stable. So in order for a beta decay, it's going to have to release its electron and convert that neutron into a proton. It then changes its neutron to proton ratio and is hopefully within the stability range. Otherwise, it's going to have to go through another beta decay. So how do we know what a beta decay looks like? Well, we see that 0, -1 beta icon. Okay, that's the loss of an electron. So we had our carbon atom, 14,6 carbon. Okay, and that's going to decay into 14,7 nitrogen. Whoa. How did we go from 6 protons to 7 protons? I thought mass had to be conserved. Well, notice on our beta particle, okay, it is a -1. And on our right side of the equation and on our left side equation, our masses are going to equal and our protons are going to equal. So if we add our atomic masses up, we got 14 on both sides. Well, if we take on our protons, if we take our nitrogen 7 and our beta particle -1, that's going to give us 6 protons overall, which is the same amount we have with our carbon. So just remember, everything equals out. The law of conservation of mass goes through on everything. So alpha particle, 4,2 helium, beta particle, 0, -1 beta sign. Now we go to gamma decay, okay? Gamma decay releases gamma rays, and these are high energy electromagnetic waves that are emitted from the nucleus as it changes its energy state. Okay, just like we talked about with valence electrons, they have different energy states or levels in which they can have. There's a theory out there that the nucleus has different energy levels within itself as well. We won't go that far in this class. As far as close as we get to that is gamma decay. Okay, key thing with gamma decay is this emission usually occurs immediately following some other type of decay. It does not affect the overall numbers involved. It's just saying, hey, there was this energy release. That's just being more accurate of a equation. So for instance, we have our polonium alpha decay problem again. Okay, we'd have that, and to be more accurate, we want to show that there was a gamma decay at the end. Okay, so we just put our gamma signal 0, 0. Because it has a 0, 0, it's not going to affect the overall conservation of mass. But it's just stating that to show that, hey, there was some radiation that left the particles, or radiation that left the atoms. So now that was the alpha, beta, and gamma decay. Let's talk about positron emission. Okay, so notice first of all with the sign here, it looks a lot like a beta decay sign, except instead of a -1, we have a +1 at the bottom. Okay, so hang on to that. Nuclides below the band of stability, so beta decay was above the band of stability, positron is below the band of stability. Nuclides below the band of stability are unstable because their neutron to proton ratio is too small, so they need to increase that ratio. To decrease the number of protons, a proton can be converted into a neutron by emitting a positron. Okay, so what happens here? An atom, it has too low of a neutron to proton ratio, so it emits our positron, and our positron basically converts a proton to a neutron, and then the positron leaves. Okay, positrons are particles that have the same mass as electron but have a positive charge and are emitted from the nucleus in the same kind of radioactive decay. So let's see about this. So if we have a positron emission, it's going to be below our delta stability, so below the 1-to-1 ratio. So our potassium-38, it's going to decompose into argon-38 and a positron. Okay, so if we add our atomic masses up, we still have 38 on the left side and the right side. But let's pay attention here. Our argon is 18. If we add our positron to it, the +1, then that's going to give us our potassium's 19. So again, mass is accounted for. So just to reiterate, when it is below, when the ratio of neutrons to protons is below the band of stability, then a positron could have the possibility of being emitted. It tries to decrease the number of protons by converting them into a neutron and emitting a positron. Another type of decay or another type of radiation is electron capture. This happens when we have a neutron to proton ratio being below the band of stability. Okay, so just like positrons, if it's below the band of stability, this can happen. Basically, what happens here is that an inner orbital of the electron orbital, so the inner layer, they take an electron, the nucleus is going to take an electron from that layer and then convert it into a neutron. Okay, so our symbol for this is, for our electron being lost, is E with a -1. Pay close attention to that -1 is going to play a key role in a minute. So we got our silver 106, and it has 47 protons. We do an electron capture on it, so that's going to remove an electron, turn it to a neutron. Okay, in order to account for the same mass, so to have a law of conservation of mass, the 106's to be equal, then that means we're going to have to remove a proton, so that's going to give us 46 protons with PD. Okay, now if we just look at both sides, if we add them up, they're going to be equal. So that's electron capture. Our final topic today is half-life. Okay, so what is half-life? What's the big deal about it? Well, no two radioactive isotopes decay at the same rate. So one might be decaying a lot faster than the other or slower than the other. Because of that, we use half-life to show the time it's required to decay exactly 1/2 of that atom, okay, or 1/2 of that isotope. So if we want to take, for instance, our circle, if we want to say the half-life of it, then it can convert to half a circle. Well, if we want to do another half-life, then we're going to have to convert that to 1/4 of a total circle, okay, just illustration's sake. Now, here's the key thing to keep in mind. You might write this formula down. The half-life, the number of cycles for a half-life, the equation is the time elapsed multiplied by 1 over the isotope's half-life. Okay, so the half-life of the isotope is going to be given to you, and you're going to multiply the time that has elapsed times 1 over that isotope's half-life. So the time it would take to decompose half of it. So let's put this into practice. Let's work a problem. Phosphorus-32 has a half-life of 14.3 days. If you start with 4 milligrams of phosphorus-32, then how many milligrams of phosphorus-32 remains after 57.2 days? So what we're going to have to do, first of all, is figure out how many cycles happened. Okay, in order to figure out how much we have left, we need to figure out how much it was divided by 2, or how many half-lives it was happened. So we figured out how many cycles. So we do our formula. of how many days it is, so 57.2 days, and we multiply it by 1 over its half-life. So multiplied by 1 over 14.3 days. When we do that, we get that it has 4 cycles that it goes through, or 4 half-lives. So now all we have to do is take our initial mass or weight of our phosphorus 32 and multiply it by 1/2 4 times. Not 4 times 1/2, multiply it by half. So 4 times 1/2, that's 2. Then we do it again, so that was 1 time. 2 times 1/2 is 1. That's 2 times. Then we do it again. 1 times 1/2 is 0.5. Okay, and then for a 4th time, 0.5 times 1/2 is 0.25. So we have 0.25 milligrams left over after 57.2 days. So that's how we got to work these problems out. I hope this helped you out. We'll have a lot of practice problems with this, so please refer back to the practice problem video so that you can see how half-life works out, how alpha, beta, gamma decay work out, how proton emission or electron capture and positron emission work out, and all that. And saying that, keep up the good work and see you next time.